Let's talk about the Doppler effect. The main idea behind the Doppler effect is that if we have some object that is producing waves of some kind, whether that be sound waves, which is what we're focusing on here, or even other waves like light or waves in a lake, we're going to see the effect that motion has on those waves. So let's start with our most simple situation. Let's imagine we just have like a pond. We'll have a big pond. And we just have like somebody sticks their finger in the water and they're just dipping it in and out. And as they remain stationary, and the only motion is the motion that's going to make the waves, we're going to get the ripples that spread out on the pond from that point source. Or we could also think if we had like a tap that was dripping into a sink, nothing's moving, and we're just going to have a whole bunch of concentric waves that are originating and spreading out from that point. The question we want to deal with now is what happens if that point starts moving? So let's take a step backwards in time, and let's take a look at a series of snapshots. So we're going to have time 1. The dot is at our source of the waves at this point, and we're going to produce a wave. In the next snapshot of time, we're going to jump forward in time, and we've moved. So when we make our next wave, we've moved a little bit ahead. And again, make another wave. We keep moving. And if we accelerate, we start going faster. We start going further during each time. The waves are going to kind of spread out and change shape. So this is just a quick rough drawing. Let's take a look at a little animation to get a better view of what's happening. This here is an animation showing the same thing that I was roughly trying to draw. So basically we're going to notice that instead of there just being nice concentric clean rings around the source, as we're moving, the waves in front of our direction of motion, so if we're heading forward, the waves in front of us are getting compressed. Basically they don't have time to form, or like we're outpacing them, so we're running toward the wave that we just produced. So instead of having a nice clean ring, we're kind of keeping up with the ring that's extending in front of us. And so the waves in front are going to be compressed, and meanwhile behind, the waves are going to become more stretched out. There's going to be a greater distance between their peaks and troughs. The waves behind us are going to have a greater wavelength. So we're going to have shorter wavelength in front of us because we're racing toward them, and we're kind of pulling the waves away with us, so to speak, behind us. And so we're going to have a greater wavelength back there. Let's take a look at a couple other animations. This animation is basically the same as the previous one, except we can see that we have two observers. So this is going to tell us something about, we're just focusing on sound here, the sound that each observer is going to proceed. So let's deal with the front observer first. The front observer is in front of the source. So the source is rushing in the direction toward the front observer. That means that the waves being produced in the region to the right are more compressed together, and so they're going to have a shorter wavelength. However, the observer in the back, they're going to experience the longer wavelengths because the source is moving away from them. So two different observers, both observing the exact same object, maybe a car driving past, or somebody playing a musical instrument, or something. Generally cars where we experience it, or some kind of vehicle, car, train, plane, something that moves quickly. And so if we're in front of it, we're going to hear a more high-pitched sound because the wavelengths are shorter, whereas someone behind, or notice even the same observer at the front, after the source passes them, they begin to experience the longer wavelengths and the lower frequencies. And we can take this to an extreme where eventually you'll see the source is outpacing the waves. It's going so fast that the waves are only generating behind them and kind of creating a wake. So if you see kind of the V shape formed behind the source, that's the same thing that happens in the lake when you are driving a boat. Basically, if you just, drop a rock in the water of the lake and the ripples start to head out, they're just going to travel at a certain speed, and that's like the natural speed of waves in that medium, in that lake. But when you drive the boat, you go faster than that. You drive faster than the waves can be produced, and waves can naturally travel. And so they build up in behind, and just like the wake of the boat, that's the same thing that we see here. So you can see as the source is moving quickly, that there's no waves in front of it anymore. They're all behind because they're going too fast, just like when you're on the lake driving the boat. There's no real waves in front of the boat anymore. They're all behind. You can see they build up and produce that wake, and then as that wake, that zone of compressed air and sound waves reaches the observer, that's when we experience a sonic boom. I did find one more animation simulator thing online that I thought was pretty useful, so let's take a look at that as well. And here we observe the same thing. The green bar represents the observer, the blue dot represents the source, and this one's kind of slowed down a little bit so we can see it a little more easier. That as our source is moving in some direction, the waves in front of it in the direction of motion are more compressed, and so the observer is going to experience those shorter wavelengths, that higher frequency. As the source passes it by, because of the motion of the object, the source is going to experience those longer wavelengths and that lower frequency. And we've all experienced this in real life. We've just maybe never known the name for it. So if you've ever watched like a car racing, or especially if you watch like IndyCar or something that goes really quickly, or you hear a plane coming or something, and you kind of hear it go like, meow. That's the Doppler effect. That's the high frequency as it approaches you, and then the lower frequency as it passes you. So all of that is great in terms of a qualitative understanding. So all of that's great in terms of a qualitative understanding of how the Doppler effect works, but let's get a little more quantitative. Let's bring some math into it and see how we can actually calculate and do some analysis with this type of thing. So let's start by looking at the equation that we're going to use for working with the Doppler effect. And our formula is going to look something like this. The shifted frequency, so the frequency that we observe when the moving vehicle passes us or whatever it is going to equal to the product of the velocity of the sound times the frequency of the sound being emitted by the object, so like the pitch of the engine or the note being played by the musical instrument, divided by the velocity of the sound plus the velocity of the object, or minus the velocity of the object. If you haven't seen this notation before, it's basically a way of writing two separate equations. So basically we can think of this as being two equations. One that looks like this, I'm just going to use short forms to write quickly, or the alternate form of the equation, Vs frequency over Vs minus V object. And the question now is, how do I know which version of the equation to use? So I'm just going to clean up my highlighting here for a moment. And we'll just make a little note off to the side to help us remember that we are going to use plus when the sound is moving away from us, or the source is moving away, and the minus when it's moving toward. Now let's take a look at the questions that are provided in the content section on Brightspace, and let's try to answer them together. So the answers are provided, but once again, it's helpful just to have a voice talking through it rather than reading it on our own sometimes. Rather than show it on the screen, I'm just going to kind of read and summarize, and then we'll write down our variables as we go. So in the example we're given, we're talking about a siren on a police car, and we're told that the siren has a frequency of 1024 hertz. So let's start by that. So we're going to have our emitted frequency, or the frequency of our source sound, is going to be 1024 hertz. At 0 degrees Celsius, we could label the wavelengths of the sound as 32 centimeters. Do we need the wavelength anywhere here in this equation? It doesn't look like it. I think it's just adding extra information to help us get an understanding of sound waves. Let's discuss what happens as the source is approaching. So we're standing there, and our totally awesome police car is going to be coming toward us. What else do we need to know? So we know that the waves are going to be compressed, so we expect the frequency to be higher than what is being emitted. And let's take a look at our piece of information together. So the question says the air temperature was 0 degrees Celsius. So that means we can calculate the speed of sound based on work we've seen previously. And we're going to see that the velocity, technically the magnitude of the velocity, because we aren't worried about direction here, or like we're not including it as a vector quantity, is 332 meters per second. The car is moving, so the velocity of the object producing the sound is going to be 180 kilometers an hour, or 50 meters per second. Make sure our units need to match. So if you're working through this question and you see that it's 180 kilometers per hour, remember we can't work with the units like that. We need to convert them. And the question asks us, what is the frequency that the boy hears? So we're trying to find our shifted frequency right here. So let's plug in our values and see what we get. So I'm just going to move this out of the way, give myself a little bit more room to work. All right, let's work with our equation. F shifted is equal to velocity of the sound, which is 332 meters per second. That's 0 degrees out. The emitted frequency is 1024 hertz. Velocity of the sound is 332 meters per second. And are we going to add or are we going to subtract? We're going to subtract because the object is moving toward us. So subtract, and velocity of the object. Object is the object that's producing the sound. So that's the car. So these are all our pieces right here. So let's do the calculation. We're going to have 332 times 1024 divided by 332 minus 50. It's going to give us a value of 1205.6. And so we're going to round, and our shifted frequency is going to be 1206 hertz. And just like we expect from our previous experience, we expect it to be a higher frequency. It's not a lot higher. So the actual source, the siren on the police car, is producing a tone at 1024 hertz. As it's approaching us, it's not going that fast. 180 kilometers is pretty fast. Kilometers per hour is pretty fast, but it's not like a plane or anything. And so the shift is only going to be by 2 hertz. All right, let's take a look at our next question. What happens after the vehicle passes? Well, let's do another calculation. Once again, we're trying to determine what is the shifted frequency that's perceived by our observer. So it's going to go past. So we're going to have, once again, we're just going to go through our equation and sub in our values. Velocity of the sound is still 332 meters per second. Frequency emitted is still 1024 hertz. Divided by velocity of the sound, 332 meters per second. Minus the velocity of the object. Oops, sorry. We did minus last time. We're moving away now. The car has passed us. And so we're going to add instead of subtract. And we're going to add the 50. Now let's calculate. 332 times 1024 divided by 332 plus 50, and that's going to give us a value of 889.97, or we'll just round. 890 hertz. And I just realized I made a mistake when I was discussing here. For some reason, I only looked at the last digit, and I was like, oh, it only went up by 2. That's wrong. You can clearly see it's gone up by almost 200 hertz, so it is quite noticeable. And then same thing as it goes past, once again, instead of being at 1024, it's at 890. So in each case, it's gone up by like over 100 hertz. So that would be quite noticeable, and you definitely hear that sound that we expect. And I think that's about all this lesson asks us to do in terms of Doppler effect calculations. Basically, this is the only equation that we're going to use. We could be asked to find any one of these variables, so make sure your skills are up to snuff in terms of rearranging equations. So if it asked you to find the emitted frequency, if we knew everything else, then we would have to rearrange. But ultimately in this course, I believe this is the only equation we need to use. So just get a feel for it, work through the example and check your understanding questions and such, and make sure you feel confident using this equation.